Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 7 of a unit current electricity. So let's begin with today's class. In today's class we are going to discuss about the electric cells. So let's begin with the electric cell. Now what is electric cell? We can say it's a device in which a constant potential difference is maintained between its terminals, either by chemical reaction or by mechanical actions. Maybe either by chemical reactions, you understood and you studied this in chemistry as well, that what electric cell is, what voltaic cells, and what other cells. Yes, so what primarily we know about the cell is that, let's suppose this is the structure of an electric cell. This is a structure of an electric cell that we develop a constant potential difference at this point of time by somehow, so that it can do some work. Yes, a cell mainly having a two terminals. This is the first terminal, this is the second terminal. You can say this is the first terminal, this is the second terminal, and one of the terminal which is having a higher potential difference is called as a positive terminal, and other terminal which is having a lower potential is considered as a negative potential. So this is positive terminal of the battery, this is the negative terminal of the batteries. And ability of an electric cell to drive the charges in a circuit is called as an EMF of a cell. Very important. We are going to discuss about the two parts. One is the EMF, another is the potential difference. So what is EMF? It is the ability of an electric cell to drive the charges in a circuit, that we call as an EMF. Yes, let's look at the one very important parameter of an electric cell. It's an internal resistance. Now what internal resistance is? So let's look at this. This are the first terminal, this are the second terminals, and this is electrolytes. I hope you understand what electrolytes, and this two are the electrodes. So when there is a connection, or when the circuit has been connected, a certain resistance is offered by this electrolytes and electrodes of a cell. This resistance provided by electrolyte and electrode is known as the internal resistance of a cell. So we cannot have all the energies that we have designed our cell for, because certain potential drop would be always there in the internal resistance, and that drop is wasted and that cannot be converted to an energy. I hope those things are clear. Yes, so now let's look at this, what electromotive force EMF is all about. The EMF of a cell is called 1 volt if 1 joule of work is performed by the cell to drive 1 coulomb of charge once round the circuit. What is it? It's something like this only. V is equals to work done by charge. This is EMF, this is work done of 1 joule, and this is charge of 1 coulomb that has been passed from this, and this. Yes, this is the work done. It's an EMF of a cell is called as a 1 volt if 1 joule of work is performed by the cell to drive 1 coulomb of charge once rounds the circuit. So V is equals to work done by charge, and its unit of EMF, it's in volt. Dimension you can calculate easily. It's an M1 L2 T minus 3 A to the power minus 1. This is EMF, electromotive force. And the second terminal, it's a terminal potential difference. Now what the terminal potential difference is? It is the potential difference between two poles of a cell in a closed circuit. When I say in a closed circuit, I mean when current is drawn from the cell is called the terminal potential difference. So here very important difference is, if current is being passed through circuit, it is potential difference, or terminal potential difference, and if current is not being passed through circuit, then it is EMF. I hope you are clear with this too. What is EMF and what is potential difference? If current is not being passed through circuit and you are measuring certain potential difference across the two terminals of a cell, then it's an EMF, it's an electromotive force. But if current is being passed through the circuit and you are measuring up the potential drop or potential difference between the two terminals of a cell, then it is the terminal potential difference or terminal voltage or a potential difference across the cells. I hope these things are clear. So now let's just try to derive the relation between EMF of a cell and the potential difference between its two terminals. So now look at this. This is the cell EMF, it's an E. Internal resistance has been shown, and this network, that means this cell has been connected. This is probably the positive terminal, this is negative terminal, and this terminal has been connected with certain external resistance R. So what I need to, it's an V should be is equals to work done by charge. So if I write down the every work done, the energy spent in sending the charge through the external resistance, this is R. This work done, it's a for E, it's a Q into E. For this voltage, it's a voltage across the internal resistance R, it's a Q into V. And for this potential drop, it is equals to Q into capital V. I hope these things are clear. Is it clear? Yes. Any issue in this? No. So what, according to the law of conservation of energy, total amount of energy was this, it's a Q into E, that has been supplied to two people, one at the internal resistance, another at the external resistance. So this Q into E is equals to Q into capital V plus Q into V. This Q has gone, and what we are having, it's a E is equals to V plus V. So if I write this potential difference, it's a potential difference across resistance R. Shall I write this? It's a PD across resistance R. A small v, it's a potential difference across small r. Yes. So I know that V is equals to I into R. So if I write it's a V is equals to E minus V, I can have this V is equals to E minus IR. This is the relation, V is equals to E minus I into R. If you observe this very carefully, then you might have an idea that in most of the cases, terminal potential difference or terminal voltage of a cell is always less than the EMF of a cell. When I say always, here I am considering approximately 98 to 99%. Which are the remaining percentage? We are going to discuss it in the next slides. But at this point of time, you can remember that V is equals to E minus IR, where V is the terminal voltage, E is the EMF, I and R you know. So this is the case, this is the relation between terminal voltage and EMF of a cell, that is V is equals to E minus of IR. Is it clear? Let's look at certain MCQs and we will get back to this. The SI unit of terminal potential difference, it's in voltage. Yes, do it very quickly, do it fast, it is just the theoretical aspects. Next, the dimensional formula for terminal potential difference. How should I do this? It's a V should be is equals to work done by charge. Work done can be written as a force into displacement Q. It's a coulomb. I is equals to Q by T. So Q is equals to I into T. Now force. Force is the MA. It's a kg into meter divided by second square. Distance or displacement, it's a meter. I into T, it's an ampere into second. So this would be kg multiplied by meter into meter, which is a meter square, divided by ampere multiplied by second cube. So this is equals to m1 L2 t minus 3 and a to the power minus 1. This is the answer. I hope you got this. Is it? Is it? Are you sure? Great. So now let's look at the charging and discharging of electric cell, open circuit and short circuit. So at the very first I'm going to discuss the charging and discharging of electric cell. But before we start this, let's have some more basics to the electric circuits. Let's say that this is terminal A, this is terminal B. While I write VAB, I mean it's a potential difference. Potential difference across A and B, that we write as in VAB is equals to, let's suppose this is E. That means potential difference between these two terminals is of E. So I can write like this, it's a VAB that would be equals to plus E. Now suppose a situation is something like this. And even this is of E. So what I can write, it's a VAB that should be is equals to minus of E. Now why this happens? Because this is a terminal A has been connected with the negative polarity of the battery, while B has been connected with the positive polarity of battery. So what you need to do while you write VAB, you are moving from A to B. So if we make a certain kind of thumb rules, I hope you clear with the thumb rules that you need to follow it. If we are moving from point 1 to 2 and positive terminal of battery is available, we consider it as positive voltage, otherwise negative voltage. I hope these things are clear. So if you are moving from A to B and you stuck with the positive terminal of the battery, consider it as a positive. And if you are moving from A to B and here you are stuck with the negative terminal of the battery, consider it as a negative. I hope those things are clear. Is it clear? Okay. Now one more thing. Observe this very carefully. It is something like this, that this is E1, this is, let's say, R1, this is E2, this is E3, this is point A, this is point B. Let's suppose current is flowing in this direction. So as you can see, it's in series combination, so current would be the same. Current I is passing through this. At this position, at this point of time, I would just assume the direction of current, and I don't know how this current arises, but I know that this is the situation. So one more convention we are going to write is that if we move in the direction of current, we will take I into R as positive, and if we are moving in the opposite direction, if we are moving in the opposite direction of the current, we will take I into R as negative. Is it clear? Yes. So read it again and again. If we move in the direction of current, we will take I into R as a positive, and if we are moving in the opposite direction of the current, then we will take IR as a negative. I hope those things are clear. So if I write VAB, it's a potential difference across AB. Let's say this is VAB. That is equals to, if I'm started moving from here, first what I get a battery. It's a positive terminal of negative terminal. It's a positive, so I should write it's a plus E1. Then what I get? Resistance. So for resistance I need to write I into R, because V is equals to IR. So am I moving in the same direction as current is flowing, or in the opposite direction in the same direction? So what I need to write, if we move in the direction of the current, we will take IR as a positive. That means I will write it as an I into R1. Then a battery, positive terminal, negative terminal, it's a positive terminal, that is plus E2. Then again go ahead, it's a negative terminal, it is a minus of E3, and that's it. You did it. Is it clear? Is it clear? Is it absolutely clear? So can we do this kind of questions? Can we? Let's have a look. First, you just practice it to write down the equations. We don't want to find out the values. We are just interested at this point of time to find out the relations. So let's suppose it is A, this is B, and this is E1, this is R1, this is E2, this is R2, this is E3. Now let's suppose current is flowing in this direction, and value of current is given as an I, and you required to find out VAB. So what you need to do, suppose you want to move from VAB, so let's write it down. Then it's a, we are starting from A and moving towards the B. So this is, first I will stuck with the battery, it's a positive terminal of the battery, so I write it's a plus E1. Now I am moving in this direction, and current is moving in this direction. So there is, we are moving in the opposite direction, and as we are moving in the opposite direction, we need to take it as a minus. It's a negative, minus of I into R1. Then I stuck with the negative terminal of the battery, this is minus of E2. Then again I stuck with the negative of direction of the current, it's a minus of I into R2. Then it's a plus E3, and that's it. You did it. Great job. I hope these things are clear. Is it clear? Yes? Do you enjoy this? Okay. Let's have a look to the new question. Suppose this is A, this is B, this is of 5 volt, this is of 2 ohm, 3 volt, 1 ohm, 4 volt, and 2 volt, and current is moving, let's suppose current is moving in this direction, and current is of 2 ampere. You need to find out VBA. It's a terminal voltage between E and A. How could you do this? So first we need to move from B to A. So while I started moving from B to A, first I stuck with the battery, and it is a negative terminal of the battery. So this is of minus of 2 volt, then it's a plus of 4 volt, then it's an, we are moving in the same direction as current is moving, so it is a I into R, then it's a plus 3 volt. Let's suppose this is R1, this is R2, so this is I into R1, then it's a plus I into R2, then it's a minus of 5, and that's it. So this is minus of 2 plus 4 plus current, it's a 2 ampere multiplied by 1 ohm, it's a 2 plus 3 plus 2 ampere multiplied by 2, it's a 4 minus of 5. So this is equals to, minus 2 plus 2 has gone, 4 plus 3 7, 7 plus 4 11, 11 minus 5, it's a plus 6 volt. This would be the answer. I hope these things are clear. Is it clear? Yes. So can you do this kind of questions? Are you sure? Yes. So let's have a look. Situation is something like this. Yes. This is A, this is B, this is of 8 volt, this is of 2 ohm, this is of 3 ohm, this is of 4 volt. As this is the battery which will lead, so current will be moving in this direction, and I am supposed to find out VAB. Let's say current is of 2 ampere. So while calculating VAB, what I can write, it's a VAB. So I need to start from here. It's a VAB. That means I am moving in this direction. First stuck with the battery, and it's a positive terminal of the battery, so it is a plus 4 volt. Then in the opposite direction of the current, so this is minus of I into R1. This is R1, this is R2. Then again in the opposite direction of the resist current, it's a I into R2, and then positive terminal of the battery, it's a plus 8 volt. So this is plus 4 minus of current. Current is of 2 ampere, resistance is of 3 ampere, it's a 3 ohm, sorry, minus of, it's a 2 multiplied by 2, it's a minus of 4 plus 8. So this plus 4 minus 4 has gone, plus 8 minus 6, this is plus 2 voltage. I hope those things are clear. Yes. Does it clear? Great. So now let's back to the charging and discharging of a cell. Now you might get an idea that why we were discussing those terms and those relations. So let's have a look at first at the discharging of a cell. It is the situation when current is drawn from a cell, and current inside the cell is from cathode to anode, and current outside the cell is from anode to cathode. This you know from the chemistry point of view. You know that electrolytes would be there, and electrolytes will passes of ions would be there, and all that stuff. Yes. So in this case EMF is more than the terminal voltage, but how this arise, we don't know at this point of time. So let's have a look that this is the positive terminal of the battery. Let's say this is the positive terminal of the battery, and this has been connected with certain resistance R, and the thing is something like this. Let's suppose this is terminal A, this is terminal B, and as it is a battery, it is moving in this direction. Yes, here the battery has been shown. When it represents like this, it's an E comma R. That means if I break this, or if I see this by a magnifying glass, it represents something like this. It's an E and R. I hope these things are clear. So while I am moving from A to B, while I am moving from A to B, what I can write? It's a VAB, that would be equals to, I am moving in this direction. It's an opposite direction than the direction of current. First I stuck with the positive terminal of the battery. It is a plus E. Now a resistance would be there, but current is moving in this direction and I am moving in this direction. So these two are the opposite. It's a minus of I into R. So this terminal potential difference arise, which is of V is equals to E minus IR. And in this case, terminal voltage is always less than or equals to E. When it would be an equal to E? If R is equals to 0. If internal resistance equals to 0, then V is equals to E, which is not possible in practical life. Yes, internal resistance is always there, but if it is there, yes, we can go for it. But in reality, it's a V is equals to E minus IR always when it is a case of a discharging of a cell. Is it clear? So when it is a case of discharging of a cell, it would be an V is equals to E minus IR. That means terminal voltage is less than the EMF of a cell. I hope those things are clear. Next, let's look at the charging of a cell. So when current is sent into a cell, it is said to be in a charging condition, and current inside cell is carried from anode to cathode. And in this case, potential difference across its terminals is greater than the EMF of a cell. But how this can be achieved? Let's have a look. That suppose this is the cell to which I want to charge, and it is being charged by certain master battery, or you can say master cell, like this. So this is our cell which is in charging, and this is, let's say, E externalite, give it a name, and current will be flowing through this in this direction. This is I, this is the A, this is the B. So while I write from A to B, while I write VAB, then it could be written as, look at this, that I am moving from A to B, and while I'm moving I stuck with the battery positive terminal, it's a plus E, and I am moving in the same direction, it's a plus IR. Look at this. This is the rare case where terminal voltage is greater than E. So this is the case if cell is being charged. This is the case if cell is being charged. So if it is the case of the charging of a cell, if it is the case of a charging of a case, it's a V is equals to E plus IR, and if it is a discharging of a cell, it's a V is equals to E minus IR. Yes, so let me summarize this. So summary of charging and discharging of a cell. So if it is the case of a charging of a cell, then V is equals to E plus I into R. So here terminal voltage is greater than or equals to EMF. This is the terminal voltage, and this is the EMF of a cell. And if it's a discharging of a cell, then this V is equals to E minus of IR, where V is less than or equals to E. I hope these things are clear. Is it clear? Is it? So if it is the case of a charging of a cell, it's a V is equals to E plus IR, and if it is the case of V discharging of a cell, it is a V is equals to E minus IR. But this is the exceptional case, but it is there. but it is there. So if they say that terminal voltage is always less than the EMF of a cell, it is not 100% correct. I hope these things are clear. That's why when we discuss in the previous slides, look at this. When we discuss at this point of time, the statement is always is not 100% correct. That's why I've written it's a 98 to 99 percentage. This 98 to 99 percentage case is of discharging of a cell. So when my cell is being discharged, its terminal voltage is less than the EMF of a cell. But if my cell is being charged, its terminal voltage is greater than or equals to EMF. Equal to term would be always there when R would be equals to 0, that you know. Now is it clear? I hope the things are clear. Yes. So this is all about the charging and discharging of a cell. We are going to do the numericals of the same, but before that we just want to discuss the open circuit and the short circuit. So let's understand what open circuit is. We said that if the terminals of the cell are left open or cell is connected to an infinite external resistance, then the circuit is said to be open circuit. Here I should be 0 and V is equals to E. So the situation would be something like this, that suppose this is the internal resistance of a cell, this is the EMF or the battery, and this is something like this. So as you say, this is the open terminal and current can only pass through the circuit if it finds closed path. Here current is not having any closed path. So when I write terminal voltage, it is V is equals to E minus of IR. But as my current is 0, in this situation V must be equals to E. So terminal voltage or potential difference, it is the same thing. So if you measure somehow, it is a VAB. If you measure somehow VAB, then you can find it out the EMF. It's an electromotive force of a cell. How could I do this? We have a one device which we call as a potentiometer. We are going to learn about the potentiometer in the coming classes. That means in the coming lectures of this unit only. Yes, but potentiometer is there which can calculate potential difference or which can measure EMF as well of the cell. And to measure the EMF, we kept potentiometer. Please remember this. Okay, so at this point of time, let's move on. So if terminals are open, or one more case is, let's suppose this is E, this is R, and this has been connected with the resistance R. This R tends to infinite. I hope you understand tends to infinite, that is it is nearly infinite. So even in this case I equals to 0, and if I equals to 0, my V should be equals to E. Yes, so this is open circuit. Is it clear? Now let's discuss the short circuit of a cell. This is very interesting, and examiner use the concept of short circuit very interestingly in the series and parallel combination of resistors as well. Yes, even we are going to see some of the numericals of short circuit. But what is it? If both the terminals of a cell are directly connected with a conducting wire, then the cell is said to be short circuited. In this case, the current through the circuit is maximum while terminal voltage is 0. So the situation is let's suppose you understand this is point A, this is point B, and this is the cell, but you have connected one wire and just bypass the cell. Now what I mean by a bypassing a cell or short circuited the cell is, let's suppose some current is passing through here. When current reaching here, it is having a two option, either to go through this path, it's a path number 1, or either to go through this path, it's a path number 2. Now current will be always having a tendency, it is always having a tendency to pass through the path which is having lower resistance. So this is the wire, and in ideal situation we considered the resistance of a wire as a 0. So if it is having a zero resistance, all the current will pass through a path 1 only, and there is nothing to be passed through path 2. So this is what we call as a short circuiting of a cell. In this case, voltage is 0. Yes, and current could be the maximum. It's an I is equals to E by R. Is it clear? Is it clear? Are you sure what short circuit is all about? Great. Now let's look at the last concluding slide. It's a percentage of total energy which is used in driving the current, or I need to find out the efficiency of the cell. This is very, very important. This has been asked, efficiency of the cell, 3 times in J main examination. So please look at this very carefully. It is about to find out the efficiency of a cell. Now when I say efficiency, what my mean always is, what we are always interested in, that efficiency is always about the output divided by input. It is always the output divided by input, and if you require in percentage, it would be n multiplied by 100. So what we get as in an output, it's a terminal voltage. What we provide as an input, it's an EMF. So V is equals to IR, and for EMF is equals to I into bracket R plus R. This has gone, and this is R divided by R plus R. So if I write down this in a percentage manner, it's 100 into capital R. When I say capital R, I am talking about the external resistance, and when I say small r, it is the internal resistance of cell. It is the internal resistance of a cell. So this is 100 into capital R divided by R plus R. So this is the case. And thus you can calculate the efficiency of the cell. So is it clear? Can you do this? Now let's look the summary between EMF of a cell and potential difference. This is very important topic for the board examinations. Very, very important. It's very important topic for the board examinations. Please go through this and remember this. Yes, we have discussed all the things. Of difference between the EMF and potential difference. So let's look at this very quickly. EMF is the maximum potential difference between the two electrodes of the cell when no current is drawn from the cell when the circuit is open, while the potential difference, it is the difference of the potentials between any 2 points in a closed circuit. This is what we discussed in the first slide. Second, EMF is independent of the resistance of the circuit, but potential difference is proportional to the resistance because it is a V is equals to E minus IR, and it depends on this. The term EMF is used only for the source of EMF, and potential difference, it is measured between any 2 points of the circuit. EMF, it is the greater than the potential difference between any 2 points in the circuit. This is we are discussing for the discharging of a cell, and potential difference is greater than EMF when the cell is being charged. Yes, I hope this is clear and you can remember this easily. So let's again look to the certain questions. Let's have a look. the terminal difference or the terminal potential difference is 0 when it's a closed circuit, open circuit, short circuit. Yes, short circuit is the case when terminal difference or the terminal potential difference is 0. Look at the next question. In the case of a short circuit, the current is in the case of a short circuit the current is maximum because resistance is 0 or resistance is very less. And when resistance is very less, current in this case will be the maximum. I hope these things are clear. Is it clear? Okay. Any doubts? Any doubts on this? No? So shall we move further to the grouping of the cells? Shall we? Let's have a look. It's a grouping of the cells. When we say grouping of the cells, we are going to group the cells in two manners. One would be the series grouping of the cells, such as the resistors. It's a series combination of resistance. This is series combination of the cells. And one more, it's a parallel grouping of the cells, or it's a parallel combination of the cells. Yes, so let's begin. It's a series combinations of cells of different EMFs and internal resistance. So first, let's look at the diagram. We have n number of cells, first, second, third, and n. Each one is having an EMF of E1, R1. Another cell, it's an EMF of E2, R2, E3, R3, and so on, En, Rn. And this circuit has been connected with external resistance R, and the potential drop or potential difference across the external resistance R is V. Now I know that V is equals to E minus IR, because this is the case where we are getting an energy from this grouping of the cells. So these cells are being discharged, and this is the case of the discharging of a cell. That's why V is equals to E minus of IR. And when it is the case, the terminal potential difference across every cell, let's suppose I write it's a V1, this as a V2, this as a Vn. Then according to the standard formula, I can write like this: it's a V1 is equals to E1 minus of I1 R1. Same way, Vn is equals to En minus of In into Rn. So this is V1, which is E1 minus IR1. It is a V2, which is E2 minus IR2, and onwards it will move on. So if I write down the net potential difference for the combination, I can write like this: it's a V equivalent is equals to E equivalent minus I into R equivalent. Now I know that every current would be the equal. Why? Because it is the series combination I remains the same. So I1, I2, I3 and In, they are the same, and V equivalent would be equals to V1 plus V2 plus V3 up to Vn. So when I write like this, I am having a relation which says that E equivalent would be E1 plus E2 plus E3 up to En, and R equivalent would be equals to R1 plus R2 plus R3 up to Rn. And my current, it would be constant. How could I calculate it? It's a V minus E by R that I understand. I hope this is clear. Is it clear? Is it? Any doubts on this? Is there any doubts in this? Let's conclude and summarize certain things. These are very, very important for competitive examination point of view. Please remember. So this is first, it's a rule for series combination can clearly be extended to any number of cells. That's why we have taken n number of cells. And the equivalent EMF of a series combination of n cell is same as the sum of their individual EMFs, that we know that E equivalent is equals to addition of all the cells, E1 plus E2 plus E3 plus E4 up to En. This is the E equivalent. and the equivalent internal resistance of a series combination of n cells, that is the R equivalent. It's a equivalent of internal resistance of a cell, which is R1 plus R2 plus R3 plus R4 and up to, this can be extended up to Rn. So this is the E equivalent and this is the R equivalent. We can go through this. So this is the series combination of a cell where more than one cells are being connected in the series, and we are just going to find it out, the E equivalent and R equivalent. Yes. Now let's move to the second phase of the grouping. It's a parallel combination of the cell. This is parallel combinations of cells of different EMFs and internal resistance. Let's look at the diagram. It's this are connected as this is E1 R1, E2 R2, E3 R3, and same way as an EN RN. And this complete network has been connected with the external resistance R, and the potential difference across this external resistance is V. So consider this parallel combination of different cells as shown in the figure. I am sure that you have gone through this derivations in your theory sessions as well. Yes, that's why we did this very rapidly. So in parallel combinations, what I know, it's an I equivalent would be equals to I1 plus I2 plus I3 up to IN, and as they are the parallel combinations, it's their V would be equal. So what I can write, it's a V is equals to E minus IR. So this is equals to IR is equals to E minus of V, and my I is equals to E minus of V divided by R. So this is the relation where I can find out the current. It's an I is equals to E minus V by R. In the next slide, I have written the solution of this. It's an I1, I2, I3, and so on. It's an IN. And while solving this, I am having this relations that I am having this relation which is E equivalent. The equivalent EMF can be calculated as this is equals to E1 by R1 plus E2 by R2 plus E3 by R3 up to En by Rn, divide by 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. This is the E equivalent when cells are connected in parallel. I hope those things are clear. And to calculate the 1 by R equivalent, it's a 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. So this is how you can calculate E equivalent and R equivalent when cells are connected in parallel. So is it clear? Is that clear? Are you sure? Can we do this? Okay. Let's look at this question. They says that for a cell which is charging in a circuit, it's charging. When I say it's a charging, I mean V is equals to E plus IR. That means my terminal voltage must be greater than E. This would be the answer. Now suppose if they says for a cell which is discharging in a circuit, what should I do? It's a V is equals to E minus of IR. That means V must be less than E. Yes. Let's look at the second question. The internal resistance of a cell depends on its concentration of electrolyte, distance between the electrodes, area of electrodes. This depends on all this. Yes, please remember. Next, when the cells are arranged in series. So when cells are arranged in series, E equivalent would be E1 plus E2 plus E3 plus E4 up to En, and my R equivalent will be equals to R1 plus R2 plus R3 up to Rn. Yes, so their EMF increases. The current capacity we don't know because we don't know about the R equivalent. Yes, so but we are sure for this, it's an E equivalent. So this is the case when cells are arranged in series, their E equivalent will increases, so its EMF increases. I hope these things are clear. Is it clear? Great. So shall we move to the next? We have a certain questions. Suppose this is the situation. This is the cell of 8 volt and this is its internal resistance of 2 ohm. This is another cell. This is another cell of 5 volt and this is its internal resistance. This is of 3 ohm and this resistance is of 8 ohm. So they says find out current flowing through this circuit. This is the requirement, find out current flowing through this circuit. So first, whether the cells are connected in series or parallel. As I can see that, look at this from here A to B. As we are moving in this, a same current will be flowing through each of the cell, or different current is flowing. Let's suppose this is current I, the same current I is flowing through this. Yes, and if both the cells are or when current is same through both the cells must be in series. And if they are in series, first find it out the E equivalent. Now how could I find out the E equivalent? It's an 8 volt and 5 volt. They are connected like this. A negative terminal of the first has been connected with the positive terminal of the second, and so on. So this can be written as E1 plus E2, which is 8 plus 5, which is a 13 volt. This is the E equivalent. Now calculate the R equivalent. It's two resistors, they are connected in series. This is R1, this is R2. So R equivalent would be equals to R1 plus R2, which will give me a 2 ohm and 3 ohm. It's a 2 plus 3, which will be an 5 ohm. So the circuit would be, it's a 13 volt, this is 5 ohm, and this is of 8 ohm. So the current will be 13 divided by 8 plus 5. This is 13 by 13, which should be a 1 ampere. This should be the answer. Yes, do you understand this? Are you sure? Can you able to solve this kind of questions? Can you? Let's have a look to some more questions. Suppose the situation is something like this, that this is the first cell and this is its internal resistance. This is the second cell and its internal resistance. This is the third cell, its internal resistance. This is the fourth cell and its internal resistance. The thing is something like this. This is A, this is B, this is E1, R1, E2, R2, E3, R3, E4 and R4. Now I require two things. It's an E equivalent and R equivalent. This is what my requirement is. Let's do it very quickly. Let's do it. So how could I find it out? E equivalent. Now first thing, whether this all are connected in series or parallel. So if I observe this very carefully, current will be going through all will be the same, and if current is passing through each one, and the same current is passing through each one, that means this all are connected in series. But as they are connected in series, look at this, it's a negative terminal of the second has been connected with the positive. I am only interested in E equivalent, so that's why I am drawing only the cells. So negative terminal of the first cell is connected with the positive terminal of the second. Same way, negative terminal of the second has been connected with the positive terminal of the third. But here, two negative terminals are connected. This is E1, this is E2, this is E3, this is E4. So this is A, this is B. If you go from the EAP, what will you write? Remember, before charging and discharging of a cell, we have derived this. It's an, if you are moving from this and you stuck with the battery's positive terminal, you need to write it as a positive. It's a plus E1, then it's a plus E2, then it's a plus E3, but here it's a minus of E4. So please do remember this as a thumb rule, that for series combination, one of the terminal of previous battery should be connected with the another opposite terminal of the next battery. That means negative terminal of this has been connected with the positive, then they are added. But if two negative terminals are connected or two positive terminals are connected, that means they are in opposite polarity, so they are going to subtract it. And what about the R equivalent? Resistance have no polarity, they are just going to add it up. It's an R1, R2, R3, R4 and onwards. I hope these things are clear. Is it clear? Any doubts? Anything? No? Great. Let's have a look to the questions. It's a E comma R. Again it's an E comma R, E comma R, E comma R. It's a E comma R. When I write E comma R, we already discussed one more time here. It is something like this, that E and R. This is the short form. Yes, it's a VAB. So I am interested in again two things. It's an E equivalent and R equivalent. So how could I calculate first E equivalent? For E equivalent, it's an plus E, this is plus E, this is plus E, because negative has been connected with the positive, negative has been connected with the positive, negative has been connected with the positive, but here negative has been connected with the negative, so this is minus of E. So it would be equals to E plus E plus E plus E, which is 4E minus E, which is 3E. And my R equivalent will be equals to R plus R plus R plus R plus R, which is a 5R. I hope these things are clear. Is it? Now for this, I am having one more magical thing. It's an E equivalent. It's an E equivalent. That should be is equals to N minus 2 into M multiplied by E, where N is the total number of cells connected and M is the total number of wrongly connected cells. Yes, where N is the total number of cells that are connected and M is the total number of wrongly connected cells. While I am talking about the wrongly connected cells, it means their polarity has been reversed. So if you do this with this question as well, then it would be E equivalent is equals to total number of cells 1 2 3 4 5. It's a 5 minus of 2 multiplied by one cell is wrongly connected multiplied by E. It's a 3E. That's it. This is your answer. So please remember this. This is very important. This is very, very important. Remember this. Yes, E equivalent is equals to N minus of 2M. N minus of 2M into E. This is total number of cells minus M is the total number of wrongly connected cells. I hope these things are clear. So is it clear? Are you sure? Can you calculate this kind of questions? Great. Now let's take one of the question of from the parallel combinations of the cells. Let's say this is 6 volt, 2 ohm. This is 6 volt, 2 ohm. This is 6 volt, 2 ohm. And this total network has been connected with resistance R. Now if you observe this very carefully, how could I come to know that whether it is a series or in parallel? Then look at this. Let's suppose this is current I1 that is passing, this is current I2 that is passing, this is current I3 that is passing, and this total current is I, and that I will be equals to I1 plus I2 plus I3, that you understand by a common sense. Yes, so it's an I1, I2 and I3, and the current that is passing through each cell is different one, I1, I2 and I3. So I can came to know that this all cells are connected in parallel. Now I need to find it out. The E equivalent. Find E equivalent and R equivalent of the given diagram. So what was the formula of E equivalent? What was the formula of E equivalent? Have you written it? Did you noted it down? Yes or no? No? Did you noted it down? Yes, no? No? So let me show you. Write it down. E equivalent is equals to E1 by R1 plus E2 by R2 up to En by Rn. Divide by 1 by R1 plus 1 by R2 up to 1 by Rn. And also write down this 1 by R equivalent. It is equals to 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. Write it down. Yes? Great. So let's do this. It's an E equivalent which should be equals to E1 by R1 plus E2 by R2 plus E3 by R3 divide by 1 by R1 plus 1 by R2 plus 1 by R3, which should be E1. This is of 6 by 2 plus 6 by 2 plus 6 by 2. Here I am writing plus because positive of this and positive of this is connected. Even positive of this is connected. So if negative of any of them is connected, I will write it as a minus. I hope these things are clear. Yes, divide by 1 by 2 plus 1 by 2 plus 1 by 2. This is 6 by 2, 3 plus 3 plus 3. It's a 9. Divide by 1 by 2 plus 1 by 2 plus 1 by 2. This is 3 by 2. So this is 9 into 2 divided by 3. This is 6 volt. Don't you feel very, very surprised that this E equivalent is the same as any one of them? Now why this happens? Why this happens? This is E equivalent is equals to 6 volt. Go with the basics. In parallel combination, if all cells are identical, while I say identical, that means their potential difference would be the same, as well as their internal resistance will be the same, their E equivalent will be the same as any one of it, because potential difference remains the same when it is a case of parallel combination. I hope these things are clear. Is it? So this is E equivalent. Now let's calculate the R equivalent. So 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3. This is equals to 1 by 2 plus 1 by 2 plus 1 by 2, and that should be is equals to 3 by 2. So this R equivalent would be equals to R by 3. You can do the same thing. You can do the same thing while calculate it's an R equivalent is equals to R by N. This is R divided by 3 ohm. I hope these things are clear. Is it? Is it clear? Is it clear? Okay. So shall I add something to this? Shall I? Let's suppose I want to calculate this I. So in previous question, calculate capital I, or I can say it's an I total. So this is I is equals to E equivalent divided by R equivalent plus R. The E equivalent, it was 6 volt. The R equivalent, it's an R by 3, and my internal resistance is of 2 ohm. So it's a 2 by 3. It's a 2 by 3 plus R. This is the answer. I hope these things are clear. Is it clear? Is it? Any issues in this? Anything? No? Great. Now next question. Let us suppose this is E1, this is R1, this is E2, this is R2, and this has been connected with R, and you want to find out the E equivalent. That find E equivalent. So the situation is E equivalent is equals to E1 by R1 plus, as positive are connected, I can write as a plus E2 by R2 divide by 1 by R1 plus 1 by R2. So this is equals to, if I try to solve this, it's an E1 R2 plus E2 R1 divide by R1 R2 divide by, it's an R2 plus R1 divide by R1 R2. So this 2 would be a cancelled out, and this E equivalent will be E1 R2 plus E2 R1 divide by R1 plus R2. This is the E equivalent. You can remember this because this will make your task much faster. But limitation, this is applicable to 2 cells only. Yes, for more than 2 you need to stick with the basics, but when and when 2 cells are there, this will save time for us for sure. I hope the things are clear. Is it clear? Is it clear? Okay, one more. Let's suppose this is E1, this is R1, this is E2, this is R2, and this is R, and they say find E equivalent. So look at this. Here positive terminal of the first battery has been connected with the negative, and negative terminal of the first battery has been connected with the positive terminal. So while calculating E equivalent, I need to put up a minus sign. But how? Let's have a look. It's an E1 by R1 minus of E2 by R2 divide by 1 by R1 plus 1 by R2. So that should be is equals to E1 R2 minus of E2 by R1 divide by R1 plus R2. This is E equivalent. I hope these things are clear. Any doubts with this? Is there anything? Is there anything that you don't know? No? Great. So let's wind it up the session over here only. Yes, we were discussing about the cells and then the combinations of the cell. But this is very primary informations about the cells. In the next session, we are going to learn certain advanced applications and advanced numericals of the electric cells. So before you tune it to that, please assure that you know all these basics and you have been passed through very little and but for sure certain questions of the cells. While I say certain, I mean it's at least 25 to 30 questions or of very primary concepts. Please do it. This will help you guys to do this certain advanced applications. But these are the basics, these are the fundamentals, and before this we should not turn on to the next lecture. Please revise this. Please do this. This will help us. Thank you. Have a good day. Take care. Bye.